Today, we're going to prove the theorem for the sum of squares of the first finite integers. 1 squared plus 2 squared plus 3 squared all the way up to n squared. This is n times n plus 1 times 2n plus 1 over 6. Fairly sure that's the formula. Okay, and this is a fact or a theorem, and we're going to prove it. And we're going to do it by mathematical induction on the integer n. First, we need a starting point. Let n be 1. So, what will this side be? The answer is, it'll be 1 squared, or 1. And does it equal to the other side? Namely this. Now, all I'm going to do is write 1 for n. So, it's n times n plus 1 times 2 times n plus 1 all over 6. Well, that factor is 1. That factor is 2. 2 plus 1 is 3. That factor is 3. In fact, the whole numerator is 6. Over 6, it does equal 1. So in fact, the equal sign is valid. So the formula works for n equals 1. Now, out of nowhere, we are going to assume that the formula is true for n equals k. That is, instead of n, I'm going to write k. I'm going to write down the whole top line all over. Except instead of n, I write k. 1 squared plus 2 squared all the way up to n squared is equal to n times n plus 1 times 2n plus 1 all over 6. And we're allowed to assume that this equal sign is valid. It's only valid for k equals 1, because that's what we proved it for. Let me rephrase that statement. So far, we only know that it's true for k equals 1. Now, we want to show that this is also true for not k, but the next integer. We want to show for n is equal to k plus 1 the following. So instead of n, I'm in the top line, instead of n, I'm going to write k plus 1. So 1 squared plus 2 squared all the way up to n squared. N squared. So this is how I write n. N squared. And this is equal to n times n plus 1. Just write n this way. N plus 1 times 2 times n k plus 1 plus 1. But due to lack of space, let me write this down again. It equals to equals to n times n plus 1, n plus 1 times 2 times k, 2 times n plus 1 over 6, which becomes k plus 1, k plus 1 plus 1, k plus 2. You have distributing the 2, you have 2k plus 2 plus 1 is plus 3 over 6. So I need to show that this equal sign is valid. That's really what I want to show. I'm allowed to use my assumption. I'm allowed to use that. If I only add the squares up to k, I can use that. Well, 1 squared plus 2 squared all the way up to k plus 1 squared. Well, the number before k plus 1 is k squared. So I have this. And this equals, well, I have a nice rule for that. It's k times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared. Now, what I can do is, to get common denominators, I can multiply by 1 at 6 over 6. So now I have the common denominator. So I have to add, because it says add, I just have to add these two numerators. Well, they both have k plus 1 in common. What's left over? K times 2k plus 1, k times 2k plus 1, plus the 6, and I only factored out one of the k plus 1s, so I have another one left, k plus 1. So this is k plus 1 times something else all over 6. What is that something else? Well, you have 2k squares, you have plus k, plus another 6k, why that's 7k, plus 6. Now, it turns out that you can factor that second set of brackets. K plus 1, however you factor that, over 6. But it turns out that you can factor this as k plus 2 times 2k plus 3. And if you don't believe that, well, there's the 2k squared. Here's 3k plus 4 more k. That's 7k plus the 6. That's exactly what we were supposed to get. And what we wanted to show is that the sum of the squares of the sum of the first k integers, which is this right here, is supposed to show that it equals to this. But that's exactly what I've gotten. Exactly what I got. So there's your proof to show that the squares of the sum of the first k integers or first n integers really is this formula on top. That's going to finish this video. If you like problems like this, keep coming back because you can certainly expect more of this type. Please subscribe to my channel. Tell your friends and teachers and classmates about my YouTube channel. Have a great day. Thank you.